In a cyclotron, which is a type of particle accelerator, a deuteron, which is a particle with a mass equal to twice that of a proton, reaches a final speed of 10% the speed of light while moving in a circular path of a radius of 0.480 meters. All right, so the question is, what magnitude of magnetic force is required to keep the deuteron on this circular path? All right, so let's write down everything we know. We know, for starters, the velocity of the deuteron is equal to the speed of light over 10 for 10% the speed of light, which is equal to 3 times 10 to the 8th over 10. Cancel out one of these 10s here. We're left with the final velocity of the deuteron is 3 times 10 to the 7th, and this is a vector. Next thing we know is the mass of the deuteron. We know the mass of the deuteron is equal to the mass of a proton, which I have written down here, is 2 times 1.68 times 10 to the negative 27th kilograms. And also, this is meters per second. What else do we know? We know the radius of the circle is 0.480 meters, and we need to solve for the force, the centripetal force that keeps this deuteron on this circular path. For starters, we know the force equation, F equals ma. And since we're dealing with a circle here, we know that the acceleration is equal to velocity squared over the radius. And with that, we can solve for the force. F equals mv squared over r. Plugging all the numbers we have in, we get F equals our mass, which is 2 times 1.68 times 10 to the negative 27, which is 3.36 times 10 to the negative 27 kilograms times our velocity squared, which is 3 times 10 to the 7th squared meters squared per second squared, all over the radius, which is 0.480 meters. And this leaves us with a final answer of F equals, this times this divided by this, is 2.1 times 10 to the negative 19. And our units are kilograms. One of these meters cancel out. We're left with kilogram meters per second squared, which for anyone who doesn't know are newtons. And that is the force required to keep this deuteron in its circular path.